Well, thank you. And it's my pleasure to visit with everybody today to talk about some of the new feed safety research that we've been doing at K-State. My name is Dr. Cassie Jones, and I'm an associate professor in the Department of Animal Sciences and Industry, and proud to be part of our feed safety team. The first bit of news I have is great news. African swine fever virus continues to be a global challenge, but we're still free of the disease in the Americas and Australia. This is a huge credit to our producers and the efforts that they've been doing to prevent any high-risk activities and prevent the disease from coming into the US. That said, there are continued global outbreaks, especially as we look at Southeast Asia and their feral and domestic pig population, and several challenges as we look at wild boar in Eastern Europe and Africa in trying to control and understand routes of transmission. We've been part of several different opportunities in the past year to help understand what are the risks for African swine fever virus to enter the US, and what are things that we can really be spending our resources on to minimize that risk. The USDA conducted this qualitative assessment of the likelihood of ASF entry into the United States. And I want to draw your attention to the feed-specific aspects. First, feed-based entry is unlikely. However, the uncertainty is extraordinarily high. There's just not much research yet in this area. The research that we have is very preliminary, and so I think we need to continue to work in this area and understand how substantial is the risk, and if so, what are the things that we can really be doing to better manage it. The Europeans are also working on this as they're working to control and prevent transmission into their domestic herd. The European Food Safety Authority, or EFSA, is currently working on their own feed-based risk assessment for ASF transmission. And we're proud to be part of the tour of table and the experts as part of that expert elicitation. What's been really interesting to me is the risk assessment model used to establish this risk. Of course, we don't really understand or inherently know or even have enough data to be able to calculate risk of feed-based entry, but we can base it off of probabilities and this expert elicitation. What's been valuable to me is understanding how to go through the risk assessment modeling. And as you look at their equation for the probability that ASF is contaminated in the product, the probability that that contamination survives, and the probability that there's a dose that leads to infection in the pigs, this should sound pretty familiar because that risk assessment is exactly the same one that we've been using to approach feed safety for the last several years. As we've gone through this process, we've evaluated a variety of matrices, certainly including something like porcine-based ingredients, but also a variety of cereal grains and oil seeds and tubers, also compound feed, bedding, and even transport vehicles, which as what Jordan will talk about here in just a few minutes, is one of the real areas of lack of understanding that we have for feed-based transmission. As we evaluate how ASF could enter the United States, we know that there is a potential pathogen transmission route through the feed supply chain. It's unlikely, but it can certainly happen. And the way that this transmission would theoretically occur is that we could bring in a contaminated ingredient from an ASF endemic region and bring that into an ingredient facility with that contamination potentially being transported to a feed mill and then to different farms. However, I think it's also very important for us to think about backwards-based feed-based transmission, particularly as we think about something like ASF. It's possible that African swine fever virus comes in through different routes. In fact, it's much more likely. And if that's the case, the feed supply chain may still have a role, where if there's a contaminated animal at a farm, regardless of how that contamination initially occurred, we know that that transmission and disease will likely spread to the entire barn. However, during that process, there are a variety of feed deliveries to and from that farm, and that feed delivery or that feed truck goes back to the feed mill, potentially spreading contamination back to the mill, and then subsequently having risk to other production systems or other farms within that same mill network. In a worst case scenario, this risk of contamination may even extend back to ingredient facilities and trucks used to transport those, and ultimately into entire different production systems. And so understanding this risk is really paramount for us as we try to better manage our risk for feed-based transmission. We know that if porcine epidemic diarrhea virus enters a mill, it's dispersed widely. That was one of our overarching concepts that we've learned about in the last several years of feed safety research. that as soon as PEDV enters a feed mill, it goes everywhere and it spreads everywhere, and that contamination persists throughout different batches of feed. However, we had a question if this is really true for African swine fever virus. The viruses are very different. We're talking a DNA versus an RNA virus, very different stability characteristics and physical characteristics. And so we were wondering, should we even begin to test this in African swine fever virus? Is this something that producers think that we should be spending our efforts to evaluate? You overwhelmingly answered yes. So when we evaluated the top 3 priorities indicated by the pork industry during the 2020 Kansas Department of Ag Summit, we saw that the #1 priority for us to work on in the future were tools to manage a disease outbreak and protect food safety. And so because of that, we launched our largest project to date, which was evaluating the distribution of African swine fever virus within a feed mill environment following the manufacture of inoculated feed. Now you can imagine manufacturing ASF contaminated feed in Manhattan, Kansas is a bit of an undertaking in order to do it safely. So this is not done at just any feed mill. This is done at the Biosecurity Research Institute, this gated and guarded facility over here on the left side of the screen. And we are so appreciative of the BRI staff, and particularly Dr. Jürgen Richt and his team, to help lead our efforts as we transition our feed safety research into a world of unknown for us, BSL level 3 or biosafety level 3 pathogen work with African swine fever virus. This really was a team effort, because it required us within the BRI to build a feed mill. And so we can't bring a whole mill in. And so we had a mixer transported in. We connected that to a pilot scale bucket elevator and then to a discharge. Now, instead of discharging into feed trucks, which would be the norm, or even 50-pound bags, in this case, we're working in biohazard containment. And so we're in biohazard suits and respirators, and likewise, we're discharging into biohazard bags. And so we would manufacture that, seal them in biohazard bags, and set the bags aside. The first thing we wanted to evaluate was, if we introduce ASF into the environment of a feed mill, where does it go and how long does that contamination potentially persist? And so to better understand this, we had to first zone our environment. Now, what we do for this is we establish where we could find potential contamination. For example, if we're mixing feed with ASF, we know that it's most likely to find that contamination on feed contact surfaces. So the inside of the mixers, the inside of bucket elevators, the inside of the discharge, etc., that was all termed Zone A. However, we know from our previous work that contamination can spread to different surfaces outside of the direct manufacturing surfaces. And so the non-feed manufacturing surfaces that are somewhat nearby, meaning within 1 meter of manufacturing, those were considered to be Zone B. So this would be things like the floors and the walls and the outside of the manufacturing equipment, but a location where we never directly added ASF onto that surface. Finally, we have locations like the floors, walls, and equipment that's much further away, and that would be Zone C, more than 1 meter from the manufacturing location. Now, the challenge in real world situations is that these zones are not finite. They're dynamic. They're constantly moving, particularly because we have things like people and vehicles driving across receiving grates that are moving in and out from different zones. And so we term those transient zones. And so in this case, the workers, or we as the researchers who are manufacturing feed, our shoes and clothing was considered to be Zone D. So here was our process. We added feed to the mixer, mixed it for a specified period of time, conveyed it through a bucket elevator, and then discharged it into a biohazard bag. We did that initially with a batch of feed that did not contain African swine fever virus, just a normal batch of feed, because you can imagine there's some level of dust and feed residue that remains in the manufacturing equipment, and we wanted to demonstrate and have as realistic of conditions as we could. Then we manufactured a batch of feed that contained a part of that feed with African swine fever virus. So we added an ingredient to the mixer that was spiked with ASF, and then we mixed, conveyed, and distributed that into a bag, sealed it, and manufactured subsequent batches of feed that contained no added ASF. So theoretically, what we would expect would be feed and contamination on those feed surfaces after batch 2. But hopefully after batch 3, we would no longer have African swine fever virus contamination in the manufacturing equipment or within the environment. So let's see what we found. This is the impact of manufacturing sequence and sampling on the prevalence of ASF presence during feed manufacture. So along the y-axis, I have the prevalence of ASF on surfaces, and then along the x-axis, I have the manufacturing sequence. So first, the batch of ASF negative feed, then the surfaces immediately after manufacturing ASF positive feed, and then after sequence 1, 2, 3, and 4. And again, those were ASF negative batches of feed. So initially, let's look at zone 1, or the feed contact surfaces. As we would expect, we did not have any contamination after the negative batch of feed, but almost 80% of our feed contact surfaces were contaminated after the positive batch of feed. That means that after we manufactured that positive batch of ASF, we had about 80% of those surfaces, the inside of the mixer, the inside of the conveyors, that we were able to detect ASF DNA. Now, theoretically, if we were manufacturing feed with a different contaminant like a medicated feed additive or even some type of mycotoxin, we would expect that we could push this contamination through or out during the manufacturing process. That's what we do with medicated feed sequencing all the time, and why we have sequencing protocols set up within our feed mills. However, what you can see through the feed contact surfaces all the way through batch 4 is that contamination, while it was initially reduced, persisted all the way through manufacturing, demonstrating that there really is a risk for those surfaces to become contaminated within the manufacturing system and that contamination to persist. It's not inherently pushed out as it would be for something like a medicated feed additive. Now, perhaps something that's more interesting as well is to evaluate the prevalence on non-feed contact surfaces. So these would be things like the outside of the equipment, nearby and far away locations like floors and walls and ceilings, where we never directly added ASF, but perhaps ASF was accumulating there because of potential dust-borne transmission. And in fact, what we found was very similar to what we had previously seen with PEDV. That as soon as we introduce ASF into the manufacturing environment, that contamination begins to be distributed throughout the manufacturing environment, not just on the feed contact surfaces, but even outside of those surfaces. And perhaps one of the most concerning aspects is what occurs within our transient surfaces or worker shoes. As soon as we added African swine fever virus to a batch of feed, all of our workers became contaminated unintentionally with ASF, and that contamination persisted across multiple batches of feed. Now that's the prevalence. I think it's also important to pair this with understanding the quantity of virus, because we know that the dose is important as we evaluate the probability of infection. As we evaluate the potential dose on both feed contact surfaces, as well as those non-contact surfaces, and on worker shoes, we see that there continues to be a zone by batch interaction, and that the quantity of genomic copies, or the quantity of African swine fever virus DNA, continues to be high throughout all of the manufacturing process. The level of contamination really doesn't change very substantially. Now, in this case, we don't inherently know the infectious dose based on manufacturing dust. However, we do know that the mean titer of oral fluid in infected pigs is about 10 to the 4.7 or 4.78. And so we're anticipating that the levels that we found of ASF contamination and their ability to persist certainly begins to approach those that are likely or have the potential to cause infection. So what are the implications of this research? Well, unfortunately, what we found that if ASF is introduced to a feed mill, ASF can be easily distributed within a feed manufacturing facility, and that distribution and contamination can persist through multiple batches of feed. It does not get flushed through the system like it might with a different type of feed additive. That means that contamination has the potential to extend to multiple pigs and/or multiple farms, because we're not just talking about the high-risk product manufactured during that specific batch, but subsequent batches of feed that are being delivered potentially to different farms and different facilities. Because of that, we're really going to emphasize that biosecurity measures to prevent ASF transmission must include transient surfaces. Perhaps the most alarming thing for me on this was the level of contamination that we found on our own researchers or on our workers, and how that contamination persisted across all the manufacturing processes. This is actually pairing quite nicely with what Jordan will talk about in some of our epidemiological investigations with Vietnam, where it's these transient surfaces, whether they're feed vehicles or people, that are really one of the biggest causes of concern for potential ASF transmission within a feed mill. So what can we do? Well, we have a multifaceted approach to continue to prevent ASF from entering the US or North America altogether. I suggest we continue to exclude high-risk ingredients. I think we've made a strong case for extending biosecurity practices from farms to mills. And in cases of concern, we need to be looking at active mitigation, whether that's thermal or chemical in nature. In order to help producers better understand this, we've recently released a variety of different feed safety bulletins or producer publications. And then this one is Feed Biosecurity for Swine Producers. They're available now at www.ksuswine.org. And we have some coming up shortly for Feed Biosecurity for Swine Veterinarians, as well as Biosecurity for Feed Mills. This really takes a lot of our previous findings and a lot of our research from the past 5 to 7 years in feed safety and translates it into a frequently asked questions type of document that we believe is most helpful for either swine producers, swine veterinarians, or feed mills as they're trying to establish and understand how to implement feed biosecurity and feed safety within their own facilities. So with that, it's my pleasure to turn things over to Dr. Jordan Gebhardt. As we described yesterday, we're thrilled to have Jordan as part of our team. He is an assistant professor in diagnostic medicine pathobiology, as both a DVM and a PhD from Kansas State University, and he's the newest member of our feed safety team. He'll be describing the latest findings from the K-State Vietnam partnership. Jordan, off to you.